An echo. Okay, so we're in a new room, which feels slightly weird. Let's go. Okay, so what's the plan for today? So I'll remind you of these three lemmas that we need to prove, and then we'll try and prove them. Okay. So so maybe I'll start with a picture, just to remind you of what everything is. X, here's Y, A up here is red to everything, blue down here is blue to X. Right, and what are the three lemmas we're going to prove? So number one is about the size of Y. So we want the size of Y to go down by a factor of error term, P0 to the S plus T. So what is S? So the final size of A is going to be T. Maybe I'll put it somewhere else. Okay. So okay, well, I'll say it in a second. What should I say it? Okay. So what we're going to do, we're going to have various kind of steps. So R are going to be a set of red steps. And the size of R is going to be T, okay? Which is the same thing as the final size of A. Right, so remember in a red step, what did we do? In a red step, we took a vertex of X and we put it in A, right? And then we shrunk X to the red neighborhood and Y to the red neighborhood. And we're also going to have B is going to be the set of big blue steps. Right. And what do we know about B? We know it's at most. So we showed last time that each big blue step, what was a big blue step? We would find inside here a blue book S T, where S was size like L to the 1/4. Right? We put S into B and replaced X by T. So every time we do a big blue step, we put L to the 1/4 vertices in B. So how many big blue steps can we do? L to the 3/4, right? We can, because we know that we can only add L vertices in total to B without making a blue clique of size L. Okay. We're also going to have a set S of density boost steps. So what was a density boost step? That was when we couldn't do a big blue step because there weren't enough vertices of high blue degree. So we pick our central vertex X, had a red neighborhood and a blue neighborhood. We knew the blue neighborhood was small, so perhaps I'll draw the red neighborhood and the blue neighborhood. Blue, red. Okay, this guy's big. It's got a red neighborhood over here, which has size like P times Y. We said the density between these two was less than P minus alpha. So if it's bigger than P minus alpha, we do a red step. Less than P minus alpha, we do a density boost step, which means we replace X by this neighborhood here and Y by this red neighborhood. We got some increase in the density between these two. Okay. And let's call the number of these things S. Okay. So S is the number of density boost steps. And then D, which are degree regularization steps. Okay. And these are the ones we do at the start of every round. So we do a degree regularization meaning we throw away from x every vertex with low red degree to y, and then we do one of the other steps. So the steps always go D, then one of these three. Then D, then one of these three. Okay, we alternate. Okay, so now I can come back to this lemma. So we start out with y being of size n over 2, let's say. So we start out by taking it to an equipartition. In every red step, we have to go into the red neighborhood over here. And in every density boost step, we have to go into the red neighborhood here. So in each of those, we're going to lose a factor of maybe of p. And let's try and show that really p is not going to decrease, but it's going to be much smaller than p0, the initial red density. So we're going to be able to prove this with just some error here, the form 2 to the little OK. Okay. So to do this, it's going to be enough to show, so to prove this, let me try and make this slightly prettier. Slightly. Yeah, it's going to be enough to show that p does not decrease much below p0. Okay? Okay, so that's going to be sort of the simplest task. It's going to follow from the definitions. Let's write down here. Lemma 2 is going to be a bound on x, which is a bit more complicated. So x is going to go down when we do a red step. Then we know this is at most mu. What's the definition of mu? This is at least 1 minus mu times the size of x. So it's going to be 1 minus mu to the power t, the number of red steps. We're also going to do some big blue steps. We lose a factor of mu every time we do one of those. So maybe we lose a mu to the L. Right? Sorry, we lose a factor of mu for each vertex we put in. And then we're also going to lose in the density boost steps. So we're going to lose a factor of, extra factor of beta over mu for each of them on average. So recall times n. And I forgot the 2 to the little OK. So a tiny bit more space. 2 to the little OK times this guy, where beta is, so beta minus 1 is 1 over the size of S star, sum of 1 over beta I in S star, where S star is the subset of S of density boost steps that are kind of typical. They're not too big. Okay, we'll just define it properly in a bit later. Okay. Okay, so we're happy with this? Perhaps I'll get rid of this until later. We'll just say, okay.
We also show that the density boost steps that are not typical are few or something.
Yeah, right. So we're going to say there are very few very big density boost steps, which kind of makes sense, right? I mean, if you did too many of them, you'd fall off the edge. Yeah, and so they won't matter too much. So they will all be absorbed in this 2 to the little OK. Yeah. Okay, and because we're winning in the end by exponential factors, this little OK won't bother us. Okay, is this okay? Everyone happy? Okay. And then lemma 3 is going to be, okay, so we've got this problem that we have this S here that we don't like and this S here that we don't like. So we need to say that S isn't too big. The third lemma is going to tell us it's not too big. I'm going to say that S is at most beta over 1 minus beta times t plus little OK. Okay. So once again, the little OK doesn't matter. And where is this coming from? This is basically saying that when you do a density boost step, so because the average harmonic mean, whatever, is beta, we can just imagine they're all equal to beta. And if these things are equal to beta times x and 1 minus beta times x, then a decrease in density of size alpha here corresponds to what? An increase, so this bit should be p plus, well, it should be proportional to alpha. But how much are we losing? So the number of red edges we're losing here is alpha times 1 minus beta. And what we're gaining here is whatever this is times beta. So this we should be gaining alpha times 1 minus beta over beta. Right? So for these two things to balance, a decrease here of alpha corresponds to an increase here of alpha times this 1 minus beta over beta. And therefore, so each red step down corresponds to, you know, a certain number of boost steps up, and this means they just balance. Okay. Okay, so everyone happy with everything? Great. Okay, so let's try to prove lemma 1. Okay, tell me, how would you prove lemma 1? Okay, so what do we want? We want P is at least P0 minus little o1 for at all stages of the algorithm. Right? That's basically it. That's basically what we want. Right? Because we know from the definition of the algorithm, we know that y only decreases in red steps and in density boost steps. Right? In big blue steps, it's left the same. In degree realization, it's left the same. Okay? So the only thing can happen is that we multiply by p each time, basically. Okay, not quite, because we don't get p, we get something a little bit smaller. So why is this enough? So enough since the size of the red neighborhood of x intersect y is at least what? Well, in a red or a density boost step, right, we chose x after doing degree realization. So it's at least p minus epsilon to the minus a half times alpha of p times y. Right? And how large is alpha of p? Remember that alpha of p is epsilon p minus p0 plus 1 over k. That's if p is at least p0, otherwise it's just epsilon over k. And the point is this is at most, what am I saying? At most epsilon. Right? Just because p is at most 1. Right, okay. Strictly speaking, I'm assuming p0 is bigger than 1 over k. But if p0 is smaller than 1 over k, you're in big trouble already. Right? So to be entirely precise, in the paper, the algorithm stops if p gets smaller than 1 over k. So we can assume that p0 is at least 1 over k. 1 over k is very tiny, though, right? I mean, even if you're doing r3k, then you only want to, I mean, R3k, the right density is like 1 over root n, which is like basically 1 over k.
So it stops and what happens? Or do you never get there?
You never get there. Yeah, so the point is, we prove in this lemma that we never get there, as long as our p0 is at least a constant, say. So we'll at least for this course and in the paper, we can always assume that p0 is at least a small constant. Actually, we can always assume it's at least a half.
By defining red?
Yeah, just because we always take the denser color. Yeah. Yeah, and if we're doing off diagonal, we're dealing with the denser color, so it's even denser. Yeah, if the density was below a half, what we'd really do is take some blue steps and wait till the density got higher. Yeah, so we're only ever going to apply this with P0 being at least a half. Okay? So because alpha of P is at most epsilon, this thing, and remember that epsilon is k to the minus a quarter, so this thing here is little o1. Right, this bit here. Right, because it's epsilon minus half times epsilon. Right, so as long as P is at least P0 minus little o1, the size of the red neighborhood is at least P minus little o1 times y. Right, if you take P minus little o1 to the s plus t, P is a constant, it's at least a half, so the little o1 ends up in the exponent. Right, saying that P0 minus little o1 to the s plus t equals 2 to the little ok, P0 to the s plus t. Right? Because P0 is at least a half. Let's see. Okay. Okay. Everything's happy. Okay, so we just need to prove this. Right? Okay, so I'm going to erase this. Right. So we need to think about how P changes during the proof. So how does a P change in each of these four steps? So how about in a red step? So perhaps I'm going to add some notation. I'm not completely certain. I mean, so perhaps for people who are reading the paper, this is useful. So I'll just start introducing the notation from the paper. So basically, the red steps is indexed by some numbers. So let's say that R union B union S union D is 1 over to M. Okay, so these are the indices of the steps. So step 1 is in D. Step 2 is in one of the others. All the odd steps are in D. Right? So the step corresponds to when x changes, when we update. And so let's say that in step I, you create xi. Okay? So you create the set xi and the set yi, which have density pi between them. Okay? So that's what step I means. So let's suppose that I is in R. So looking at a red step. Then what can we say about pi minus 1? How much did P change in a red step?
No more than by alpha?
Yeah, exactly. I mean, so it can change by more, but it can't decrease by more. So in fact, to say it, because actually pi is at least pi minus 1 minus alpha of pi minus 1. Right? Okay. Right, because that was how we defined the red step. Okay, very nice. What about when I is in B? Now life is a little bit more complicated. Would it be helpful if I wrote a summary of the algorithm so you can look at it? Maybe it would be helpful. Okay, so let's remind ourselves of the algorithm. So what is the book algorithm? Okay, so I won't write everything. I'll just write the summary version. So 1 is degree realization. So x goes to the set of v in x, so x in x, such that the neighborhood of x in y is at least p minus down to the minus a half alpha times y. Okay? Okay. 2 is big blue. So many vertices. So it's the blue neighborhood in X is at least mu times X. Implies choose a large blue book. T. 3, choose the central vertex. 4, red step is if pi is at least pi minus 1 minus alpha. And 5, density boost. Step. So we go into the X goes to neighborhood, the blue neighborhood of X in X, and Y goes to the red neighborhood of X in Y. Okay. Uh-huh.
And in step 2,
Yeah.
we also know the size of less than 2 because of the lemma.
Yeah, right. So large means L to the 1/4. So yeah. Anything else I should add? I mean, there's a lack of space, so yeah. We can add things as we go along, maybe, as we need them. Okay, so.
But don't we need the size of the 2 bounds?
Yeah, right. So sorry. So I'm not writing what things really are. Yeah. So T is. I mean, we need lots more things, right? I'm leaving out like half of it. Yeah. It's like almost mu to the s times size of x. Yeah. Yeah, approximately. That was my. This is my. Yeah. I mean, okay, whatever. Uh-huh. Not right now, right? Because this is just the density p. So at the moment, we're not worried about the size of x. We'll worry about the size of x later. Yeah, so here we just care about the density. How much does the density go down? Or can it go down in a blue step?
We need to use the mean degree.
Yeah, exactly. So pi is at least. Yeah, so there's a slightly subtle point here. It's the min degree from the p before we did the degree realization step. So p could go up a lot in degree realization. But so it might be sort of our p I minus 2 was here. We do degree realization. We go up by miles, because we've removed a lot of vertices, but our min degree is still down here. So we do a blue step, we might drop all the way down, oops, to here. Pi minus 1, pi. Right? So you might say, Rob, why do you do something so stupid as to allow this to happen? And the answer is, it doesn't really matter. Right? I mean, we could, of course, have done something more sensible. We could have said, look, let's take this min degree condition. If we go up by a bit, let's follow it up, right? Always have the min degree to be a bit smaller than where we currently are. It just would have been a bit uglier to write. So it was a choice that we made in the writing process. Do it like this, just to make the statement of the algorithm a bit simpler. Yeah, I think in the far off diagonal paper, we're going to do the other way just to see the difference. Okay. Anyway, So, right, so there's this slight annoyance that you might go up a lot and then down a lot. So you're not comparing with pi minus 1, you're comparing with pi minus 2. Right? So what do we have? It's at least pi minus 2 minus this guy. Right? Epsilon to the minus a half alpha of pi minus 2. Right? Okay. Right, and notice this is really true because when we do a blue step, y doesn't change. Right? We didn't go into some subset of the world. Okay? Y stayed the same. So it's the same y the whole time. Y does not can change step 1, it does not change step 2. Okay. How about when I is in S? Yeah, it should go up, right? I mean, it's called a density boost step. It would be very rude of us to call it that if it didn't go up. And so why should it go up? Because, okay, the red density went down here, so it must go up there. Okay, it's not quite so immediate, because
Avoid the vertices which are bad, but their number is small because we were not able to do the blue step.
right. So exactly. So there's there's a subtlety that P is the density to the whole of Y, and we're going to this subset of Y. Right? So we need to choose X so that this subset does not have bad red degree across. So I'll prove a little later that you can choose an X like this. The added problem that we want to avoid the vertices with high blue degree, but as Alexander said, there's few of them. So it's not really a problem. It's just a little computation. Okay, so I'll sketch this in a few minutes. Okay, perhaps when we're proving lemma 2, I'll sketch it. Okay, so all I want to assume for now is that pi is at least pi minus 1 here. Right? In fact, we get some boost, and it's going to matter how big the boost is, but it's going to matter for lemma 3. Okay, so let me postpone proving that lemma until we need it. Okay? So this will be proved later. Yeah, so it's almost obvious, but not quite. Yeah, so it requires a little bit of work. Okay. And then finally, I is in D. What can you tell me?
At least pi minus.
Yeah, exactly. And why is that? Yeah, exactly. We're removing vertices of lower degree, so obviously the density is going to go up. Yeah. I guess so. As it's true for whatever threshold you pick, but we've picked one in particular below the average, so there are definitely vertices left over. We're not removing everything. Okay. 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 So now we know how these things vary. So can you now see how to go from this to? I should maybe write what alpha is again, because I erased it. It's probably not the greatest piece of board work in the world, but okay, can you read that? Okay. Okay, so how would you deduce the lemma from these for observations? So we need to control the total decrease, right? Right, summed over all the steps. Yeah, that's a good idea. So let's recall what that is. So how many steps of size R do we have? Yeah, so T, which is at most K. Right. How many steps B of type B do we have? At most L to 3/4. And we don't really care about these, right? Because they're going up. Okay, so fine.
Maybe like if we do 2 steps at once, it's easier to count.
Yeah, absolutely. So let's think about these steps in pairs. So pairs are odd even. So we do a step that's D then red, or D then blue, or D then S. Okay? If it's D then S, it just goes up, fine. Right, if it's D then red, it goes up and then down by at most this. Okay, but there's some slight problem that now this might have gone up. And D then blue, it goes down by just this much in 2 steps. Okay. Yeah, so the problem is, to write this down, is just that alpha gets bigger as you go further up, right? So if we just try to sum up these decreases, we'll find, oh, maybe pi got really close to 1. So alpha actually got pretty big, and actually the sum of these steps is huge. Because it might have gone all the way up to 1, and then all the way back down to half again. Right?
Can we do like telescopic sum?
We are only interested in the case when B
So,
is less than P0.
yes, so both of these comments are correct, yeah. Yeah. So one comment is that, right, so really, like, as the step size gets bigger, we shouldn't count it as more. We should count it according to some sort of logarithmic scale. We'll come back to that in a second. But for this question specifically, even more important, we just don't care what happens above P0, right? It can do whatever it likes up here. Who cares? It's only when it gets below P0 that we're worried it's going to go down, right? And when it's below P0, alpha is always just epsilon over K, right? So the amount that you're going down is really only epsilon over K or root epsilon over K. And there are fewer than K steps, so you go down by almost like root epsilon, actually less because this is smaller than K. So really, you're only going to go down by like epsilon. Now, I cheated a bit there. You probably noticed. So I said, okay, we only care about when you're below here.
And the first step when we were up and then came below.
Yeah, so we care about this first step where we came below. But how far can we have come down from?
But alpha is at most epsilon, so
Yeah, alpha will be.
so it's also the low one.
Yeah, right. So we won't have come from very far above. So how do we manage to come down? Maybe we did a red step to come down. But red steps only bring you down a tiny amount. So we didn't start very far above, and so we didn't step down very much. Or we might have done a blue step to come down. So maybe we came down by as much as this much. So maybe actually alpha was a bit bigger, but it wasn't actually very much bigger, right? It was only like root epsilon over K or something bigger. Sorry, 1 over root epsilon over K. So times epsilon, it's still not very far. So this is just some silly calculation you have to do, which, I mean, I can try and write it out if you like, but it's very tedious, right? It's really just, yes, you have to worry about this first step, that your alpha didn't get too much, wasn't too much bigger. And then there's also this issue that you might say, all right, well, what if, you did some degree realization step, took you up here, and then your blue step took you down here. So really, you're losing the alpha from up there instead, right? That's what you're worried about, right? Yeah. So how you want to deal with that? So the point is, it's not that alpha, right? It's the alpha of the smaller one. Yeah. So it doesn't really matter to you. You don't care how much you went up, right? You might care here, but the amount, so alpha, so the point is alpha is increasing as a function of p only by this factor of epsilon. So it can't hurt you to go up by a long way just to make your alpha bigger to come down, right? You only come down epsilon times as much. Right? So these big degree realizations, they can't hurt you for the red steps because it only increases your alpha by this factor of epsilon, and it can't hurt you for the blue steps because it doesn't change your lower bound. Right? So neither of these things are a problem. Okay, so this is actually very easy. And that's basically the proof, right?
And this little one is like root epsilon or something like this?
It's actually epsilon. Yeah, because, so there's an epsilon here, and you're saying, oh, but there's a root epsilon here, but actually there's only this many steps. Yeah, you win by more. And actually, even that is overkill. It's just, it's because when we defined the algorithm, we allowed our initial steps to be, we allowed this to be as big as epsilon over k. We could actually have taken this smaller. Right? We didn't have to allow it to be this big. We could have put like a k squared here, and it wouldn't really have hurt us. Right? So it's just because, we can give it away. Sure.
Replace these by p0 every time. But then, if you took a less step that was like a big blue step, then you would end up with epsilon, 1 over root epsilon, right? Which is what Ron said. You have to be careful.
I don't think so, because remember, alpha is like epsilon over k. It's never smaller than that. Sorry. In the range you care about, it's like 1 over k. So a single blue step can never hurt you very much. You just never go down very much. Like when you're below p0, the point is we chose this thing to be small enough so that basically nothing happens at this point. Right? It was, so this is not really the, actually maybe this is a good thing to talk about. Because it's actually quite a sort of important idea in the proof that I don't think I emphasized before. That this epsilon over k is not the critical scale of where you don't know if you want to take a red step or a blue step. So it's basically a tiny, tiny, tiny loss in red. So your enemy is probably going to say, I'm not going to give you that tiny loss in red. I'm going to do a density boost step. And I'm going to give you a tiny density boost. Right? And the density boost didn't help you at all, so, you lost. You gave away stuff in y, you gave away stuff in x, you got essentially no density boost. Like, why did we do that? Why did we allow our enemy to hurt us like that for no gain? Basically because we don't really mind, because if he keeps doing density boost steps, then our alpha starts increasing. And at some point, alpha reaches 1 over k. That's the critical range at which the enemy doesn't know whether he wants to give us a red step or a density boost step. If he keeps giving density boost steps, he starts giving us red steps, and the other way around. So it will actually balance at that point. So what we expect to happen is we'll sort of do these density boost steps until we get to sort of alpha is like 1 over k, whatever that is. P minus P0 is 1 over epsilon k or whatever. And at this point, then we're just going to like hover around here forever. Right? That's what the enemy should probably do. Okay? And we lose a little bit here, but really not very much at all, because how many steps does it take us to get from here to here? How many steps does it take us to get from P0 to somewhere alpha is 1 over epsilon times bigger? So P minus P0 should be 1 over epsilon k, which is like 1 over k to the 3/4. And how many steps does it take? Well, every time we go up by epsilon over k, but then, so perhaps I'm not made this clear enough. This is perhaps a crucial thing. Maybe I'll get rid of this. Right. Right, so let's maybe call, so let's put Q0 equal to P0. That's like the initial step. Let's define QH to be P0 plus 1 plus epsilon to the H minus 1 over K. I want to claim that if you do, so H is for height. I want to claim this is the natural measure of the height we are above 0. So I want to claim that in a density boost step, you jump up from basically H to H plus 1. In a red step, you jump down from H plus 1 to H. If L is roughly equal to K. If L is smaller, you jump up by more things. So I want to claim that what is alpha of P, I want to say it's roughly QH minus 1 or something. If P is roughly equal to QH. Something like that. Right, so this is the scale at which we're doing. This is the height at which we're doing. And it's increasing exponentially as a function of epsilon. So let's just check if this is true, if I messed it up. So alpha of P is that guy. QH minus 1. P0 cancels, this minus 1 over K cancels. What do we get here? We get 1 plus epsilon to the H minus 1 plus epsilon to the H minus 1 over K, which is what? 1 plus epsilon to the H minus 1 times 1 plus epsilon minus 1 is epsilon, 1 plus epsilon to the H minus 1 over K. Which is what? Which I want to claim is, there's an epsilon here, that's nice. This is basically, so if QH minus P0, so epsilon is QH minus P0 plus 1 over K, except not that, H minus 1. Is that right? So H minus 1. Okay. That make sense? Okay. So right, so this alpha we defined here is actually better thought of as being sort of an alpha that just depends on what height of this ladder you're at. And a red step corresponds to going down one step of the ladder, and density boost step corresponds to going up, whatever it is, 1 minus beta over beta steps of the ladder.
Would the analysis work with this definition?
So we do it with this definition, yeah. 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 Yeah, I thought this was maybe just an easier thing to take in first. Yeah, the first time you see it. But yeah, but in the paper, it's defined as being, yeah, it's defined as this. Okay. So right, so we should think of alpha as being sort of one step on this ladder. Okay. So if you like, you can think of alpha as being, so alpha h as being epsilon, 1 plus epsilon to the h over k, where, and then alpha of p is alpha of h, where h is minimal such that p is at most qh. Right. So you just see a what between which qh and qh minus 1 is p, that tells you what h is. That's the height to which your p is at. So h of p, if you like, and then just take it to be this guy. So it's the same thing. Okay. Should I put it here? Maybe I'll put it here instead. Okay. So alpha of p equals epsilon 1 plus epsilon to the h over k, where p is at most qh. Okay, h is the current height. Okay. Right, so what was the question that motivated this? I forgot. What were we trying to do? Oh, yeah. Sorry, yeah. How many steps does it take? Yeah, so you start at P0, and you go up to some point, and then you kind of go along. And this is the point where alpha equals 1 over k. And the question was, how many steps? How many density boost steps does it take to get there? Now, each density boost step, you go up by at least 1 rung. Right? Because the alpha is chosen to go down by 1 rung. Density boosts are bigger than going down. So right, so each one is going to take you up by some decent amount. Again, we haven't proved this yet, so this will be proved later. So how many steps will it take you before you get there?
Logarithm of 2 divided by epsilon.
Yeah, exactly. Basically, log of, okay, you have to go up by some polynomial in k, something like log k. But yeah, divided by epsilon, exactly. At most. Right. That the point is that your step size is increasing exponentially.
Why logarithm of k if we substitute it into that formula? We need the 1 plus epsilon to the power h be equal to 2 to get 1 over k.
So alpha should be 1 over k.
Alpha, yeah. Okay, I see.
Uh-huh. Yeah, and also, I mean, I don't care about this log k, right? Yeah. And from our perspective, log k is the same as 2, so yeah. Yeah. Yeah, and this epsilon is actually much more painful, right? Because that's a k to the quarter. But still, we don't care, right? In particular, this is little ok, right? It takes sort of 0 time. Right. Okay, so the enemy sort of, you give away these few steps at the beginning where, your x is shrinking, your y is shrinking, you're doing something super stupid, but the point is just to create this buffer. Like, so the point is just to prevent your enemy ever being able to get this, to push the p below p0, right? It's just extremely painful for your enemy to push you down. You just can't, right? You just make sure you never go below this. So we can essentially put this floor on our density at the cost of this many steps, which is nothing.
Perhaps this will come up later in the analysis, but shouldn't this mean you win by much? I mean, this is like super giving things away. You're going to use that buffer in the end, or?
No, the buffer is just to make sure that we stay above p0.
Yeah,
Right? We only stay a tiny bit above p0, right? I mean, this is not very far above p0. It's p0 plus little o1.
but this is analyzing separately everything and et cetera. And your heuristic argument is quite convincing that, in fact, this should happen, otherwise we win by much, right?
Yeah, right. Yeah, I think so.
In fact, if you analyze things more.
But, I mean, so essentially the difference between what the analysis gives and this is 0.
Okay.
Is little OK, right? So so there's this little OK here, which comes from here, but then so I mean, what happens here, right? These aren't all red steps, right? Some of them are red steps, and some of them are density boost steps, and the proportion of the density boost is given by this, right? So this is just saying exactly. This is saying exactly. You basically do this.
We should interpret this as like, okay, we pay almost nothing to get into this zone where we're actually alternating between these two steps.
We're basically alternating.
The thing that is crucial here.
Yeah, exactly. Yeah, so I mean, obviously we don't know we're alternating. You can do a bunch of res, but on average, we get the correct proportion. And that's all we care about. Yeah, we don't care about the order in which these things happen. Yeah, and if it comes down, then whatever that helps us. If it goes up, that helps us. Like, there's nothing the enemy can do to hurt us. Right. Okay. So, so I claim that as a proof of lemma 1. Everyone happy? Modulo, yeah. So we haven't yet proved this. Yeah. Exactly. Okay. So next thing is to prove lemma 2. We'll get rid of this. Okay. So here we have to consider the various ways in which x can decrease in the 4 steps. So maybe I should actually put that over here. And then, maybe I'll just get rid of this. Actually, no, maybe it makes sense. Right? So once again, we have these 4 kinds of steps, and we were sort of interested in what happens to sort of xi versus xi minus 1. Right? And if we understand what happens to xi versus xi minus 1, then we're going to be in good shape. So if I is a red step, what can we say about xi versus xi minus 1? Yeah, exactly. Okay, and now we're done. So, okay, that's all we need to know about this. Right? Sorry? Thank you. Okay, and t steps. Okay, that's good. Okay, that's it. That was the first part. Not too difficult so far. What about blue steps? Yeah, now we care about this guy. Exactly. So xi is at least mu to the size of s bit, right? times xi minus 1 over 2. So what do we care about? What we care about is the product over I in B of xi over xi minus 1. Right? So we go to this, we take the product of all these things. What this says is this is at least what? So 2 to the minus size of b for this error times mu to the power what? L. We can do a little bit better. So, yeah, what's the total number of vertices that can be added to B in big blue steps? So you're right, it's the most L, and really it's size of B.
Size of B minus S squared.
Minus S. Yeah, because every time we do a density boost step, we add a vertex to B. And we know there are S of them, because that's what we said. Okay, so an L minus S. Okay, and this B is at most L to the 3/4, right? So this thing is 2 to the little OK. Even 2 to the little OL. Okay, so we got this term. We've got this mu to the, we've got this 1 minus mu to the t. We've got this mu to the L over minus S. So we've got this beta to the S, and everything else has to go into here. Okay.
Sorry, Ramsey.
Yeah, please.
Isn't it like size of B minus S, this over the size of S, and then it will do this L times?
Sorry, it's mu to the size of B
Minus S
minus S.
over the size of S, which is like L to 1/4 or something.
Ah, sorry, there's different S's. Yeah, sorry. Let's maybe forget this S for the minute.
Okay.
So each of these guys, just be careful about the definition of B. B are the indices. So each element of B corresponds to one big blue step.
Ah, okay, yeah.
There's a set B, and there's a set of...
Yeah, sorry, this is a curly B. And this is a beta. Yeah, sorry, this is my B, and yeah, I guess by context it's around the other curly letters, right? That's why how you can recognize it. It's a curly B. Yeah, so there's a set of indices. There are L to the 3/4 of them, and in each one you add a bunch of steps. But we don't even worry at the moment how many. We just know in total, like the sum of all those steps is at most L minus S. Right. Okay, so this is the product I in B xi over xi minus 1. Okay, so we got these two guys left over. So they're a little bit more trouble. So what happens in, sorry, this is proof number 2, I'm going to get rid of this. Yeah, what happens with these guys? So let's do maybe S first. Okay, so in S step, so what happens? Xi is equal to, well, the blue neighborhood of little xi. So let's call that beta I. So, yeah, so equal to the blue neighborhood of little xi. Sorry, this is the central vertex at step I. Intersect x, intersect x, I minus 1. Let's call that beta I, beta I times xi minus 1. Yeah.
Are we going to do this over this set of all density boost steps, or only the reasonable ones at this time?
Right. right, so good questions, let's see. Yeah. Yeah, so we're going to have the product I in S of xi over xi minus 1, right, is going to be just the product of all the bi's, right? Okay. Yeah. So, and I want to motivate why we're going to split this in two. Yeah, so perhaps we can start doing the calculation and then see where it gets stuck. So I'm not sure I can.
Do we have like a global lower bound for these beta i's because we have like a mean degree?
They're not actually betas, right? They're
No, so the betas, we have an upper bound. So we know that each step, beta I is at most mu. At most mu. But Jean's right, we're going to need a lower bound. So I think at this point, perhaps we have no choice but to prove that density boost steps really boost the density. Okay. So lemma, if I is in S, then Pi is at least Pi minus 1 plus alpha 1 minus beta I over beta I. Who is this alpha? I'll say in a second. Minus something small. So I guess actually all I really need is 1 plus its lower 1. So I'll write that. 1 plus its lower 1, alpha 1 minus beta I over beta I, where this is alpha of Pi minus 1. Let's write alpha here. Say here this is alpha of Pi minus 1. Okay, so how are we going to prove this? Maybe, what would you rather keep, the algorithm or this? I'm going to keep the algorithm. Okay, I'll get rid of this. Okay. Right, so the first thing so in the algorithm, how are we going to choose our central vertex? We chose it to be not one of these big blue sets, not one of these vertices of high degree in blue, of which there were Ramsey, so this was Ramsey k L to the 2/3, right? We know that the size of x is always at least Ramsey k L to the 3/4. Otherwise, we would stop. So there's some little tiny corner here, size Ramsey k L to the 2/3, that we're not allowed to use. But anyone here is able to be our xi. Right? What do we want? We want that when we look at the red neighborhood over here of xi, we want it to have a good density to x. Okay, so let's define the weight of x to be the sum over y in x of the weight of xy, where the weight of xy is going to be, here's y, here's our x, the red density into here, basically. So 1 over y, size of the red neighborhood of x intersect red neighborhood of y intersect y minus p times the red neighborhood of x intersect y. So let's unpack this. This guy is this one. P times this guy is how many red neighbors you expect to have in here. This is how many neighbors this guy actually has in here. Right? So it's red neighborhood in there minus what you expect. Right? And then normalized by y. Notice this is not symmetric. Right? This is an asymmetric definition. Okay. And then the weight of x is just saying summed over all y's, what is this weight? Right? What is this deviation from the expected norm? And sorry? Yeah, I'm going to sum the ones we're not allowed to use as well. Yeah, absolutely. Yeah, so thank you. Good question. Yeah, we're going to have to deal with them later. Yeah. So here is a lemma. The sum of wxy over all x and y is at least 0. Almost. So let's see. So when we sum this, we get the sum of this minus sum of this. Okay. So let's do the two things separately. So the sum over x and y of the red neighborhood of x intersect, maybe this one's easy to do. Let's do that one first. Red neighborhood of x intersect y. Okay, so I'm taking out the p and the over y. That's what? Yeah, so the y is just not doing anything, so a size of x. And the sum of x of this thing, we're just counting up all of the red edges. Red edges between x and y. Okay, which is p times x times y. Okay, so what about the other guy? Sum over x and y of the red neighborhood of x intersect the red neighborhood of y intersect y. Yeah, what you're doing with your hand, exactly. Yeah, exactly. So you're counting guys here that have an x and a y. Right? You're counting paths of length 2 that go x something y. Right? So it's the same thing as summing over z in y. Sorry, not choose 2. The red neighborhood of z in x squared. Because we're counting both way around. Because I'm counting, I'm not counting pairs, I'm counting ordered path, or ordered walks actually. So I'm also including x something x. Right, which are included in this count. Right here, x is allowed to equal y. Yeah. I mean, it's I mean, it's even, you could say it's very similar to Erdős's proof of C force, right? I mean, it goes way back, yeah. Okay, but then what's this guy? It's convexity, right? It's at least what happens when they're all equal, right? It's at least, this is, it's minimized by taking all equal to p times x. At least y times p squared times x squared. But this thing is p times x squared times y. So they differ by a factor of p, which you had here, right? So literally just this inequality means this is bigger than that. Okay? That's it. Okay? Okay, so really nothing at all. We've proved on average they're at least 0. Okay, happy? I can erase? Okay. Okay. Right, so what we'd like is, so we actually choose the central vertex to be, we choose it to be not one of these vertices, and subject to that, to maximize W of x, the weight of x. Okay? So the claim is, this implies there exists an x, so implies that the weight of xi is at least minus 1 over k squared or something. I don't know what. 20. I don't know. Whatever's enough.
In the sense that we can choose an xi of this form?
Yeah, sorry. So in the algorithm, we chose xi to maximize this weight.
Okay.
Yeah, so saying there exists one not in this set with this property. Okay. And why is that? It's just because this is a tiny, tiny, tiny fraction of the world, right? Much smaller than 1 over k to the 20. And each of these guys, what's the maximum that this guy can be? Well, how large can wxy be? Sorry. That's what I mean. Important. Yeah, sorry, so let me write that. Yeah. Sorry, the scale at which W is working is the size of x. Yeah. So, how large can wxy be, the weight of xy?
1.
At most 1, right? So how large can W be? At most size of x. So say we're much smaller than the size of x. Right. So even if these guys were all size of x, add them all up, you get tiny portion of the world times size of x. There must be someone here that's not like crazily negative. Right? If they're all more negative than this, they would outweigh this tiny set here. Okay? Just using the fact that this Ramsey number is much, much smaller than the Ramsey number L to the 3/4. Right? Okay? Okay, so basically we've just chosen this small enough so it doesn't matter. We can basically ignore it. Okay?
Why aren't we able to do better than this? I mean, intuitively, we should.
I mean, this is essentially 0. And you can't do better than 0.
I would expect zero, at least.
No, you can't guarantee 0, right? Because these vertices exist. So it could be the case these are all positive, and these are all a tiny bit negative. Right? That's allowed. Our enemy can do that to us. Right? Everything at this point is deterministic. I mean, the enemy has given you this horrible coloring. Why shouldn't they give us a coloring where large blue degree inside x correlates with large W? right? But no big deal. I mean, this is basically 0, right? Just, yeah, doesn't hurt. Yeah, I mean, it's very good that you're looking for places where you can improve. My feeling is that every place where you can improve doesn't matter. Yeah.
Why is it essential that we consider the vertices on the top?
Oh, right. So it's important that when we choose the central vertex, that it does not have large blue degree. Because we want to be able to do a density boost step, we need to be able to assume beta I is at most mu.
No, but what I'm saying is,
Sorry. And
the version of the weights. Why do we need to consider every y in x instead of only the ones? Because of the density, right? You only go for x and x and y instead of x minus this.
yeah, right. Yeah, whatever you do, you're going to lose a little bit. Yeah. Yeah. Okay, so we can basically pretend that the weight of x is 0, right? And whatever we lose is just some error term. Okay, and now we're just counting edges. I'm not sure it's even worth doing. It's completely obvious what's going to happen, right? That okay, I as an S implies that the number of red edges between the red neighborhood of xi in x and the red neighborhood of xi in y is at most this p minus alpha of p times y, times the product of these things. Right. So the fact that we're yeah, sorry, everything. Everything is I minus 1, I guess. And this is xi minus 1, and this is yi minus 1. Yeah. Sorry. So it's a big mess. This is between the red neighborhood and the red neighborhood. Yeah, I sort of don't want to write this out because it's full of horrible things like this that you just can't read, right? Yeah, so I just want to say that the red density between these sets, maybe I'll write that instead. The red density between yeah, whatever. Yeah, right. Red neighborhood of xi in x and red neighborhood of xi in y is small. So what does that tell you? It tells you that the red neighborhood here is big, right? And you just count edges and you get it, right? It's like counting edges. Count edges. Yeah. And use the fact that the W is big. Yeah. And it's a total triviality, right? That if you write it out, it takes a page, it looks ugly, but literally nothing is happening. Yeah, the slight frustrating thing about this proof is that actually if you write it out, it looks more technical than it is, but really nothing is happening in this lemma at all. Right? We're just counting.
But where does 1 plus v equal of 1 come from then?
Sorry, so the error is here. So really this error is, the bound is alpha 1 minus beta I over beta I minus W of xi over xi minus 1. Something like that. Maybe times k squared or something, I don't know. I mean, whatever, right? But right, so it's like a 1 over k to the 10 or something. right? So whatever bound you put here, you get some corresponding bound here. Yeah, it's probably even just the same. There's probably no factor of k, but who cares?
We doing this lemma to bound to get a lower bound to the product. Yeah, just to remember.
Sorry, right, yeah. So we need this here just to show that beta I can't be crazily small.
Ah, okay.
Yeah. Okay. Okay. Yeah. So and then some tiny error. Maybe I'll just ignore the tiny error completely. Right. Okay. Okay. So in particular, what does it imply? So corollary, beta I is at least
Whatever makes that thing like less than 1.
yeah, exactly. Exactly. So like 1 over k squared, for example. Yeah. Right, so that's some silly lower bound. Right? It can't be. You can't have the whole thing just completely disappears in one step. Okay. Okay. Yeah. So just because alpha, remember alpha was epsilon over k in the worst case, which is like 1 over k to the 5 over 4. Yeah. There's some stupidity. Okay. Okay. So we can throw away a small number of steps without worrying about it too much, right? And we will end up throwing away the ones where the jump is too big, where sort of you jump by much more than you're supposed to. Okay. Right. So why would that be a problem? And right. And how are we going to bound this thing? Oh, we're literally out of time. Did not realize that. Is that right? We're out of time, right? Yeah, okay. Right, so yeah, what do I want to say in the last 5 minutes? So what's the problem if beta I is very small? If you take a big jump up, right? So I guess we should think about this inequality to explain this. So imagine you're at some level, at some p, and then you take a big jump up, that's what I say. And then you take sort of a bunch of little red steps down. Right. And what I sort of want to say is that you're going to match up sort of the places where you went up with the places where you went down. So really we're going to do something crazy, right? We're going to go sort of, up, down, up, down, up, down, up, down, up. And we sort of want to say that, okay, the amount you go up corresponds to the amount you come down. And we want to do this in this kind of logarithmic scale world. Right? So the world further up is squeezed down into fewer steps. And so what that means is you can't quite just think of the world as being, if you think of the world as being flat, then this lemma is essentially just saying, However much you go up, you come down the same amount, right? That's kind of what this is saying. But that's true in flat world, and it's not true in hyperbolic world or logarithmic world or whatever it is. So it's only true locally. So if you want to sort of compare going up and going down, you can do it locally.
How do we end up at the same place when we started?
We don't. Sorry.
So it's not true that the amount of steps up is equal to the amount of steps down.
That's true. But the amount extra you go up is only going to cost you this log k over epsilon. So basically, it's going to be, there's this error term. This error term is going to include things like this log k over epsilon. But it's also going to have to deal with slightly annoying things like,
Why can't we go up to 1? I don't know. So in the logarithmic scale, 1 is incorrect, yes.
yeah, exactly. Yeah. Yeah, right. So if you did this many steps up, then you'd hit 1. Exactly. Right, so there's just some slight annoyance when you're comparing these things that if you take a big jump up, you'd be going into a different scale where the world is stretched slightly differently. And that could potentially lose you a small constant factor. And there's various ways you could deal with it. And the way we chose to deal with it was just by saying, look, those big steps are kind of stupid. There's not very many of them. We can just deal with them separately. Okay? So we just say, okay, let's just split S into two kinds of step. A moderate step, which can be actually really big, but just not so big that you change your world, stretch your world by a constant factor. And those guys we can deal with in a sort of normal way. And then the ones where your jump is so big that the world changes by some non-trivial amount, you say, okay, there's very few of them. Each one of them only costs you k squared. So they're only 2 to the little OK in total. Okay. Okay, so I got through half as much as I thought I would. So that's good. So next time, I'll try and prove this lemma, which will then motivate this thing, and then that will and prove that this is. Yeah. So what do we really want here? So here we're just going to use AMGM, if I got it the right way around. Show this is at least basically b to the size of s. Really, I mean s star, and then 2 to the little OK for things that are not in it. So these are the sort of typical guys, and then the atypical guys don't matter. Okay. So I should stop. Questions? No?
Can you say how large this moderate side is?
Oh, yeah. So the height. If the height of pi is bigger than the height of pi minus 1 plus like epsilon to the minus a quarter or something. So it should go up by like 1. If it goes up by like some power of k, then it's immoderate. Yeah, so some very large amount. Yeah. And so the number of them is like epsilon to the quarter times k. Which are very small. Yeah, this is, yeah. So this is, right, so if I is in S, then these are the guys in S star. Okay. More questions? Okay, so yeah, next time I'll hopefully get through this, and then yeah, perhaps you should tell me. Do you want to see more details of how these lemmas are proved, or are you basically just, okay, it's a bunch of calculations, let's go on to the more interesting part?
It's too complicated.
It's not complicated. I mean, it's super simple. It's just a bit boring.
I think it's good to have documented because this is
Okay. 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 So
You mean
I mean, we carry until we get to the end, right? So.
Which lemma are you talking about now?
Yeah, so we proved this. We almost proved this. We haven't proved this yet. But so we went said. And no, so now we've actually proved it, right? Yeah. So because we did this. Yeah. Yeah. So this is just comparing steps up and steps down. It's not interesting. The proof is just turn the handle. But okay, yeah. Perhaps we should document it, and then we go on to the perhaps more interesting part of how you then use these lemmas to deduce what we want. Yeah, I guess people who aren't, you guys can't fast forward me, but other people can. So. Okay, cool. So we'll carry on Friday.